Hello, today we are going to start discussing civil technology. This is a fun topic and I hope you guys enjoy this. So what is civil technology? Civil technology is a field that deals with roads, water supply, drainage, sewers, structures, buildings, and environmental issues. Basically, anything that the public uses actually falls under civil technology. A lot of these things are very relevant today because a lot of these things are involved in public safety. And with what we are dealing with right now, public safety is a large issue. So I will start off by showing you this poster, which I know I showed you already a few weeks ago, but I'd like to show it to you again. And this is a picture of the water cycle. This is very important to us because as we see in this water cycle, it is a cycle, and I'm going to start with the water being stored in the oceans. As the sun hits that water, it actually evaporates and it condenses, and I have water storage in the atmosphere, or what we like to look at as clouds. And once there is too much water in the atmosphere that the atmosphere can no longer hold on to it, it falls out of the atmosphere in the way of ice, snow, or rain, right? And that's our precipitation. Now, if at the higher elevations and if the temperature is low enough, that water is stored as ice and snow. And then it eventually runs off, it melts and runs off into streams, and some of it goes into the ground as infiltration, others go into what is called freshwater storage, stuff like ponds and lakes that we see, and other actually runs off as surface water runoff and ends up back in the oceans. This slide actually shows us why it is very important to protect the water that we have, because of that cycle. If it gets polluted in any part of that cycle, our water supplies become polluted. So where does our drinking water come from? I have the slide with the distribution of water on Earth. And in the first bar on the left, the first bar graph, we see that the oceans have 97% of the water on Earth. And then the other 3% is broken up and further into 77% of the 3% is in ice caps, glaciers, and inland seas. 22% is in groundwater, and then we have the other 1%, and then we break up that other 1%, and that's our atmosphere and soil moisture is 39%, lakes are 61%, and rivers are less than 0.4%. This becomes important because when we discuss drinking water, we will see that the ocean water is not used for drinking water for the most part because ocean water has salt in it, right? So we should not be drinking salt water, and therefore the water that we use for drinking water predominantly is coming from that other 3%. Now, in this presentation, I do talk about desalination a little bit. It is something that is done, but it is very expensive, so it is not commonly done. So where are our freshwater withdrawals? And this slide is an older slide, but the amounts haven't changed really that much. So in 1990, the surface water draw in the United States was 259 billion gallons a day, and the groundwater was 79 billion gallons a day. So from very early times, water was treated so that it could taste better or look better. I know if I handed somebody in this class a glass of water that had a brown color to it, I don't think anybody would want to drink it, even if I told you, hey, that water is totally safe. You would kind of look at me strange and say, there is no way that water is safe. I am not going to drink that water. So for a very long time, people have actually treated water. So slow sand filtration is something that's still being used today, but it actually started being used in the late 1700s. Now, chlorine started being added to water so that it could disinfect water in the early 1900s. So the slow sand filtration, having been started in the late 1700s, was not originally done to eliminate microorganisms. That's what chlorine actually will do, is kill the microorganisms, because in the 1700s, people didn't really understand microorganisms, but it started being used to get particles out of the water and to make the water look better. So the typical filtration steps, and these are a little different now from what they were in the 1700s, because water treatment in the 1700s didn't really add chemicals to it as we know them. But the typical steps is first something called coagulations. Chemicals are added to the water to form floc. The floc is a chain of particles, and what happens is then they are heavier than the water, and they drop to the bottom of the tank, and that's called sedimentation. Once I have the heavier objects out of the water, then I go through my filtration stage where I remove the smaller particles from the water. The last step in a typical filtration plant is disinfection, and that step is there to kill microorganisms in the water. So I have here a typical water treatment plant that I blatantly stole from the internet to slide. And if we start kind of in the middle on the upper part of the slide, you see a lake, and you see water is going from the lake into a couple of buildings there. And in the second building, they told you that's where they do the coagulation. It removes dirt and other particles in water. Alum and other chemicals are added in water to form sticky particles called floc. And then the combined weight of the dirt and the floc causes it to sink. And then I go through my sedimentation tank, and then I go through my filter. And the filtration, if you could look closely in that, you'll see the sand in there. And then the last step, I get disinfected. And in this drawing, they're using chlorine. Chlorine is commonly used for disinfection. But right now, there is also a move where people are using either ozone or ultraviolet light to disinfect the water. Once it's disinfected, it goes into our system, our distribution system, and generally it will be stored in storage tanks until it's needed. So that filtration step, I'll show you what's going on inside there in this diagram. So in this diagram, you see we have water coming in through the inlet pipe, which is on the right side of this drawing. And then it is going through the sand. And as it goes through the sand, particles are taken out of the water. They can't pass through the sand because they're larger than the gaps in the sand. Once it gets through the sand, then I have a layer of gravel. And at the bottom of that layer of gravel, I have a perforated drain pipe. And the water goes into that drain pipe, and then it comes out of our filtration. I mentioned desalinization. This is a diagram showing it, and I will also attach on Blackboard a video that you guys could link to see how it operates. I actually visited a desalinization plant in Tampa, Florida. They have a large desalinization plant there. Like I said, It's very expensive to do, so it's not done if there's any way to avoid it. So in this case, they actually have a combined system where they actually have a power plant, and they're using the water to cool the power plant, and they're discharging, they're getting rid of the salt, and so some of it ends up becoming drinking water. So the water draws in the ocean for the cooling purposes first, then it is piped into tanks where the filters are there to remove any particles, sand, clay, debris, and bacteria. Then it goes through a reverse osmosis filter and takes out the salt at a molecular level. And in this process, 50% of the water is processed for drinkable water. The other water has a much higher salt intake, salt quantity, and that water is actually then discharged back into the ocean. And then the volume of water in the ocean allows that salt concentration to dissipate. So I will ask you guys, I will give you the links for these videos separately, and you can please watch these videos and you'll see what I'm talking about. So where does Westchester County get our water from? Well, most of Westchester County, if you have a municipal water supply in Westchester County, you're probably actually getting water from New York City's water supply system. I am always fascinated with the foresight in New York City, where over 100 years ago they started by building these reservoirs in what was then upstate New York. And if you notice, the Croton watershed, which is the furthest south, is in Westchester County, which is where we are. And then that water is piped into New York City, and the municipalities along the way, some of them actually tap into the aqueduct and buy their water from that water supply. So what is required for me to have a municipal water supply? The first thing that I list here is a reliable source of fresh water. We are very lucky here in the northeast of the United States that we do have quite a bit of fresh water available to us. So even now we are in a drought, but we do not have any water restrictions at this point. So the first thing I need is a reliable source of fresh water. The next thing that I need are pumps to distribute that water, and pipes or distribution lines to get that water out from wherever my source is to my consumers of that water, you and I, as we open up our tap and drink our water. And then there are also water storage tanks that are in the system, and these serve two purposes. They serve to store water in case of a fire, but they're also there to maintain pressure on the system. And then I have my service lines that run from our distribution lines into our individual customers. So the two classifications of water sources are surface water, and that is just water that is on the surface, and that includes lakes, rivers, and reservoirs, and groundwater. And groundwater is water that is below the ground, or well water. So there are municipalities that actually get their water supply from wells, and there are others that get them from lakes, rivers, and reservoirs. Also, some of you, even if you're in Westchester County, may not be on a municipal water supply. I live in northern Westchester. I'm in Yorktown. I am on a municipal water supply, but there are areas of this town that have individual wells, and some of you may have individual wells. So I'd like you guys to actually find out if you are on a well or if you are on a municipal supply, and let me know in the discussion forum. So what happens with well water, you saw in that first picture that water could go through the ground. And what happens is I have rain or snow, it goes through the ground and it ends up in an area called an aquifer. And then I have an impermeable rock layer. So that impermeable means the water cannot pass through it. So when I drill a well, I tap into that aquifer because that's where my fresh water is. And then I pump it up. Now, that could be at very many different levels of feet underground, depending on where you are. So sometimes you may be able to dig a well that's fairly shallow and get fresh water. At other times, you may have to go significantly deeper to get your fresh water. There is some information on that is available. There are maps that show where the common aquifers are. Those are available to you. You can look them up and find them on the internet. So where does Westchester get its water? Most of Westchester gets its water from the New York City aqueduct system. Areas not supplied by the New York City aqueduct system have either wells or municipal reservoirs. So for some of you, it is no longer part of the public water supply in Yonkers, but as we are driving down the Sprain Parkway, Sprain Lake that's in the middle there by the golf course, that actually right now they're doing work, so there's almost no water in there. But that used to be part of Yonkers water supply. That was a reservoir for the city of Yonkers. Again, it's no longer in use, but at one point it was. So again, the demand for water. So the total withdrawals in this slide are about 407 billion gallons of water, right, being used. Total use of 94 billion gallons. So that's a lot of water that we use. How do we classify water? It's classified under what it's used for. So domestic water is used for drinking, cooking, and other household uses. Public water is used for fire protection and public buildings and uses. Commercial and industrial water is used for businesses and manufacturing process. And in all of these systems, there is also a loss due to leakage, and we have to kind of take that into account. Yes, the pipes are not 100% tight. There tends to be leaks in places, and we lose water on a daily basis. Just so you guys could get a feeling for commercial and industrial water, prior to me coming to the college, I was town engineer for the town of Greenburgh, and our largest water user, there is a Coca-Cola bottling plant on 9A, and that was our largest single industrial user of water, and they used 1 million gallons of water a day. The entire water usage of the town was approximately 8 million gallons of water a day. So we used to joke around that one of the pumps in the pump station was purely for Coca-Cola. So how much water do we tend to use every single day? So this chart is from a textbook that is used for our environmental problems class, but it gives you kind of a good way to figure out how much water we have to calculate is being used per day. So domestic water use is actually figured to be 80 gallons per capita per day, or basically 80 gallons per person per day. Commercial industrial is approximately 7 gallons per person per day. Public water use is approximately 16 gallons per day, and loss is about 14 gallons a day. So the total water use per capita is 180 gallons per day. So if I were to be designing a water system, if I know my population, I would multiply that by 180 gallons per person, and I would have to make sure I have that capacity of water supply to feed that municipality or the subdivision or an area or whatever it is. Now, I know some of you are going to argue that there is no way that you use 80 gallons per day. And maybe you personally don't, that number is an average, but I would tell you that you probably do use close to that amount of water per day. Some people will use more, some will use less, but you're probably close to that. And the reason that I say that is that there are things that you do on a daily basis that you might not think about their water use. So, for example, a shower uses about 2.5 gallons of water per minute. So if you take a 10-minute shower, right there you use 25 gallons of water. Every time, the low flow toilets, every time you flush them, you use 1.6 gallons per flush, right? So every time you flush that toilet, there goes another 1.6 gallons, right? And then in your house, you're also using water for cleaning, for washing things, for cooking, and all of that tends to add up. And even though you might not think you're using that much water, you probably are. So I mentioned our pumps, and our pumps are designed to pump the water to the highest point in the system. So they must be able to pump enough water to supply the system. Required flow must be calculated for your system, and if your system has high demands, they must be designed for. So I mentioned that we designed for 180 gallons per capita per day, but if I have an industrial area in town that uses significantly more water, I have to make sure I design for that. Also, health department regulations say that I must maintain a minimum pressure of 20 psi at the highest floor of my highest customer. Right? So because of that, that's maintained in two ways. And if you remember, I said that the water storage tanks also are designed to keep pressure on the system. So they have to be higher than the highest customer by an amount that I could guarantee that my customer gets 20 psi at the highest floor. My distribution lines must be large enough to carry water to customers without losing capacity or pressure. The line closest to the pump station are generally bigger. Residential neighborhoods can have smaller water mains. Most municipalities have a minimum pipe size of 8 inches. That was not always the case. Where I worked, like I mentioned, as a town engineer. I was also a village engineer for Groton on Hudson, and I actually worked for a private water utility, part of General Waterworks before that. And I could tell you that there are many neighborhoods, especially older neighborhoods, that have smaller water lines than the minimum of 8 inches that is required now. Many of them actually had 2-inch water lines. And one of the things that, as the engineer, that I was trying to do was eliminate those 2-inch water lines as much as possible. And we would, design and ask in our budget to replace a certain amount of those pipes every year so that we can get our system to run a little better than it did. because what happens over the years, those 2-inch water lines deteriorate. They end up with deposits inside of them, so their opening is no longer 2 inches. Water pressure drops, water capacity drops, and people will have difficulty. In some of the older neighborhoods, I would get complaints that my neighbor turns on his water and my water pressure drops. And then once we would replace the 2-inch water line with a larger water main, those issues went away. I've mentioned here that we try to avoid dead ends whenever possible. On something like a cul-de-sac, if the water main just ends at the end of the cul-de-sac, but it's not tied into anything else, that's what's called a dead end. The problem with having dead ends in your water supply system is that a cul-de-sac may not have enough demand to be drawing water all the time, and the water at the end of that main could become stagnant. And then you'll have discolored water or bad tasting water. And in general, when you have a dead end that you can't design around, the municipality will put a fire hydrant in there. First of all, to fight fires, but also it gives us a spot where you could turn on that water and get water flowing through the pipe and eliminate the discoloration. Storage tanks are used to store water for times of high demand and also when the pumps are off. The pumps don't run 24 hours a day. They're not designed for that. So what ends up happening, and I say here at the almost second to last one, they act as control points for the pumps. There are floats in the storage tanks that send a signal to the pump station. When the water hits a certain level, a low level, the signal goes on that turn the pumps on. And then once it hits a higher level, it sends a signal back to the pumps and says, okay, we have enough water, turn the pumps off. That is also done. The water going up and down in the tanks is also done so that water does not become stagnant. So there's always water flowing through that throughout the day. They supply water in the event of fire. They maintain pressure on the system, and they are at the high points of the system. Now, I mentioned to you that they supply pressure. Well, hydraulics tells us that our pressure in a system is based solely on the height of water that is above us. So like when the pumps are off, the water pressure is based purely on how tall that tank is above where I'm measuring the pressure. So I will we'll talk about that more at another time, but the height of the water above it is going to tell us what the pressure is in there, right? And so sometimes you may actually hear the term, instead of like pounds per square inch, which we're used to for water pressure, you may actually hear it in inches of water column or feet of water column. And so if you see it in inches, that's telling us that that pressure would actually have support a column of water that high. So something to think about. Again, we'll get into that more at a later date. And if you have any questions, please, please let me know in the chat room. We have our chat room there. So anyway, I'm just gonna, so let me move on. So I have here a picture of a ground tank. You guys may have seen that. Then I have here a picture of an elevated tank. You may have seen those. These are fairly common around our area. So from drinking water, we're now going to move on to stormwater, and I'm going to talk about hydrology. So hydrology is the study of the distribution and movement of water on and under the earth. I have a link here which I'll ask you guys to go into because I can't do it from the presentation, that has some areas, some conditions where Westchester has had flooding. The two extreme hydrological conditions are droughts, and droughts are times when there's not enough water, and floods are times when there is too much water. In Westchester County, we've had areas that flood, and for some reason, before I was born, I know you guys will find that hard to believe, but certain of our highways were built right along rivers. So something like the Sawmill River Parkway, the Bronx River Parkway, the Sprain Brook Parkway. Notice these are all named after bodies of water, running water. And guess what? Every one of these highways is prone to flooding because they are right next to this river, and during storms they tend to get flooded. So probably not the best idea to build them along there, but that's where they are now. And as engineers, we've been kind of stuck with finding ways to eliminate some of the flooding or getting the flooding to a more manageable level, but they do flood when there's intense rainstorms. So total land area that contributes runoff to a stream, river, or lake is called a watershed. It is also called a drainage basin, especially if it flows into a drainage system. The point of concentration or basin outlet is the point where engineers determine the amount of runoff. One of the ways that we've helped to control some of the flooding has been with regulations that require that the amount of runoff after development on a property is the same or less than the amount of runoff prior to the property. So that's why you'll see on newer subdivisions and newer developments, commercial developments and also housing developments, that there will be drainage basins of some type that are included in there so that the runoff after construction does not exceed the runoff before construction. And I will ask you guys if you notice as you're driving around any watersheds, because I mentioned earlier in this presentation that we have part of the New York City water supply here. And if you haven't noticed, I'm going to ask you to look for them. But if you're driving in certain areas near any of the reservoirs, you'll actually see signs telling you what watershed you are in. And those are there to alert people that, you know, this water is going to end up into that watershed. And please don't pollute, because it's going to end up into the drinking supply. So this is a picture of a drainage basin around two ponds, Little Bear Pond and Bear Pond. And the way we find a drainage basin and find its area is we use what's called a topographic map. This is a topographic map, so it shows the elevation. And it basically goes along the highest elevations in the area, and I draw that line around it. So you'll see that there is a line that circles the tops of the mountains and hills around the Bear Pond. basically any water or rainfall, snow that falls inside that line will end up in those ponds. Any water that goes on the outside of those lines will end up going into a different watershed. And if you look at the lower right-hand side, you will see the outlet of that pond, and that water will end up going out that way. One of my responsibilities when I was working for the towns was I had to actually look at people's plans when for subdivisions, for commercial developments, and all of that. And one of the things that they were required to do is actually show me which basin they were in, watershed they were in, and give me a map such as this so I could see where the water is going and where it's discharging from. And then also, as we'll see on the next few slides, calculate how much water is coming in and how much water is leaving. So to estimate the amount of storm runoff, the most popular formula is something called the rational formula. And the rational formula is given by Q is equal to C times I times A. So Q is the peak rate of runoff. C is something called the runoff coefficient. I is the rainfall intensity. And A is the drainage basin area. So the runoff coefficient, C, is a dimensionless number that represents the fraction of rainfall that becomes surface runoff. If all the rain were to become runoff, the C would end up being 1, and that is like something like an impervious surface. So if I have rock or clay, both of those are impervious, and the runoff would be 1. If none of the rain became runoff, C would be equal to 0. Now, in reality, for pretty much any area, the value of C is between 0 and 1, depending on the land use or the surface of that area. So our typical runoff coefficients based on what type of land we have. In woodland areas, the runoff coefficient is between 0.01 and 0.2. Grassland or lawns are 0.1 to 0.25. Pavement and roofs is 0.7 to 0.95. Now, I know you guys may be saying, well, isn't a roof and pavement impervious, so shouldn't that be 1? The answer is yes, pavement and roofs are essentially impervious, but if you ever see any type of development, I don't generally have 100% pavement. There will be a grass strip along the road, or if in my building there's going to be, even a commercial building where I have a building with its roof and then I have a parking lot, but there's going to be some grass areas in that parking lot or some dirt areas or stone areas, and that's why it's not exactly 1, it's less than 1. Suburban residential areas are 0.25 to 0.4. Apartment housing areas are 0.5 to 0.70, and industrial areas are 0.6 to 0.9. So my storm sewer consists of inlets and pipes that take runoff and bring it to a point of storage or discharge. Storm sewers are usually designed to carry water from a storm of between a 10-year and a 25-year storm, depending on the municipality. This means that during storms with more rainfall, the storm sewers will overflow. Most municipalities have a minimum pipe size for storm sewers. It can be either 18-inch or 15-inch pipe, depending on the municipality. There are different types of inlets as shown below. So I guess different municipalities like to use different types. Around here, most common is the one on the right, which is called a combined inlet, where there is a curb inlet and then also a grate. But while I was down in Delaware, I noticed that almost all of their drainage things were using basically the curb inlet, and the gutters were pointed towards those curb inlets, but there wasn't a grate there, at least in the area that I was. And then there's other areas where they have the grate, but there is no curb inlet. So there are 3 different types of storage basins. There is a retention basin, and that has some water in it all the time. A detention basin only has water for a short period of time during and after a storm. And a recharge basin is designed to allow water to recharge an aquifer. So you may have seen these. When I first got married, I was living in a condominium in Ossining, and they had a retention basin, so there was always water there. It was like a pond, but it was designed to hold the storm water there. And what these basins have is they have an outlet that is a metered outlet that allows a certain amount of water out of that basin at a time. So in that case, they were using it as also a feature of the property. There was actually a gazebo and picnic tables around that retention basin, but it also acted for stormwater. Detention basins only have water for a short period of time. Like I said, you'll also see those, and they generally will be empty unless it's raining, and then they'll be full or have some water in them depending on the storm. And the recharge basins are designed to hold water, but instead of letting it go out into the stormwater system, it goes back into the ground to recharge an aquifer. Now, I used a couple words earlier in a couple slides earlier about 10-year, 25-year storms and 100-year storms. And in this slide, I mentioned that storage basins are designed to handle a 100-year storm. Well, a 100-year storm is a storm that, in probability, will happen once every 100 years. That does not mean that it will only happen once every 100 years, because it is probability. There's a chance that it will only happen once every 100 years, but it may happen a little more frequently. And one of the things that we're hearing now with climate change is that the intensity of these storms is getting greater. Now, how much rain falls for a 100-year storm also depends on where you are. So if we go back to the rational formula, I had that it was my Q was equal to C times I times A. Well, I was my rainfall intensity, and that will be given in a unit of rainfall per period of time, right? So like inches per hour is one that we may see. So you guys know in this area, a 100-year storm is a rainfall event of approximately 8 inches of rain in 24 hours. That is a pretty significant amount of rain. Now, in the year 2000, we had 2 100-year storms within 6 months of each other, 99 to 2000. And during one of them, I know this, I was working for the towns, and the data that we had showed that we got 3.5 inches of rain in the municipality I was working in less than an hour. So that is a huge amount of rain coming down in less than an hour. And That was estimated to be approximately a 500-year storm. So our drainage structures were not really designed to handle that amount of water, and there was quite a bit of damage to the municipality after that storm. And pretty much most of Westchester County along the Hudson River saw significant amounts of damage. In Ossining, there was actually a transmission repair shop, and the cars ended up in the Hudson River during the storm. They literally floated out of the shop and into the Hudson River. It was a disaster. I actually got called out at 2 a.m. and had to have people leave their house at 2 a.m. because it was dangerous, and I couldn't really evaluate how much damage was done to their foundation. So I actually had to have them go to a safe place. We had shelter set up in the municipality so that people could get away from a dangerous situation and be somewhere safe until we could evaluate what was going on. So these basins, they're there to reduce the peak runoff, reduce flooding, reduce soil erosion, and protect the surface water quality. So one of the ways they protect surface water quality is that if the water is sitting in this basin, the heavy stuff, so any dirt and particles that are in the water, will start to drop out into the bottom of the basin, so that then the water that's discharged, that is cleaner water than what's in the basin. Now, because that drops out, these are designed to be a certain volume so that they hold the amount of water that is needed during a storm. They have to regularly be maintained because those particles that fall out will reduce over time the volume of that basin. So that's why they have to regularly be maintained. Unfortunately, maintenance is not always a high point for municipalities to do. So, you might in your career have to kind of fight to get these things maintained properly. So here's a picture of a basin, and you can see it's got water in it. It's being used almost as a nice feature here. This picture, these houses are low, so I'm going to assume this may be down in Florida, because they don't build as many taller houses because the hurricanes would damage the taller houses due to the wind. So, but it's got a nice feature of having the pond there that could be used for other purposes. So this is the end of today's presentation. I will have the links on Blackboard along with this so that you can see the videos that I was talking about. If you have any questions on any of these, please ask your questions in the chat room or send me a text message, and I will try to answer any questions that I have. Thank you very much.